Cool. So Christoph told us about the need for AGM feedback and how this energy could be imparted. One mechanism that the AGM could be imparting this energy to the hot gas. So I'm going to focus on observations, and in particular I'm going to focus on the cool and cold gas that we see in these galaxies, and what might that have to do with radium wave feedback. So I'm going to just quickly define typical properties of the systems I'm looking at. So here I'm talking about very, very massive galaxies. So we're talking about brightest group galaxies, brightest cluster galaxies. They have old stellar populations, they have small star formation rates, and I'm talking about low redshift systems. They're sitting in the centres of large potentials. They're unlikely to get wet mergers into them. So why am I talking about cool and cold gas? Surely there should be none, right? Actually, there's lots. So this is a plot of molecular gas mass against H alpha line luminosity in a lot of these systems. This is an old plot. A lot of those upper limits are now nicely sitting on this line. And it's not uncommon for these very massive galaxies to have about 10 to the 10 solar masses of molecular gas in them. So not just tenuous ionized gas, but also lots of molecular gas too. So what would we like to understand? We'd like to understand what's the relation of these cold gas phases to AGM feedback. We'd like to understand what's the origin of the gas in these galaxies. How did that gas get there? And we'd like to understand why it isn't forming stars. As an example, I'm going to take ABOL 3581. So this is actually a galaxy group. It's a cool core nearby galaxy group. So this is what it looks like with the X-ray emission over the top. And so it's a cool core group. It's one of these systems that requires heating to offset the cooling. Okay. So we have the AGM feedback, which is blowing these bubbles into the hot gas, as Christoph showed us earlier. So you can see that there are depressions in the hot gas, and these depressions can coincide with bubbles in the radio emission. So we can see the 1.4 gigahertz radio emission filling up two little X-ray cavities that are connected to the nucleus. There are also X-ray cavities further out. So there's evidence just on the side here for a ghost cavity. We don't see this in the low frequency radio emission because we haven't got observations which can go to that low frequency. And so the systems, some of these systems have multiple bubbles, and it's from these multiple bubble systems that we get our observed AGN timescales. So we look at the timescale of rising to one bubble and then the timescale for the next bubble, and you find that these timescales are typically about 10 to the 7 years. So that's very similar to the timescales we heard before when we were talking about the quasars. And it's perhaps not a surprise because what we're talking about here is a timescale where we're saying that these bubbles can rise at the sound speed in the hot gas, and we're saying that the bubbles get out to, typically in these sorts of group systems, we're seeing 10 kiloparsecs, 15 kiloparsecs maybe. So the numbers work out about the same. We also see, statistically, in AGN, the duty cycles are high looking at the X-ray data. So this is the point that Christoph was mentioning that's in contention with his M87 data. So what I'm showing here is the number of systems with cavities and the cooling times. So people have gone away and they've looked at huge numbers of these systems that are close by where we have good X-ray data and we can see these bubbles. And they look at how many they can see bubbles in. And you see bubbles in most of the systems that are X-ray bright. But there is a selection effect here, of course. If it's not X-ray bright, we can't see bubbles. So you should take that with a little bit of a pinch of salt. Okay, so I said I'll talk about cool and cold gas. So there is some residual cooling in this system. The coupling isn't 100% efficient. Some of these systems we see the cool and cold gas in. And this is one where you can see H-alpha filaments extending up to about 15 kiloparsecs out of the galaxy. The H-alpha filaments also are accompanied by dust in the system, and the dust looks like it follows the same filamentary structure in the center of the galaxy as that bright central H-alpha emission. So the cold phase in these systems are likely embedded within this warm ionized gaseous filaments too. So usually when we're talking about radio mode feedback in low redshift systems, we're talking about keeping hot gas hot. But we see cool gas in these systems, we see cold gas in these systems. So I'm going to argue here that the gas that we see in these systems is originating from the hot gas, and I'm going to argue that radio mode AGM feedback isn't just important for the quiescence part, it's also important for the quenching part. It's also helping us not form stars in these systems. Okay, so this is back to ABEL 4581, and this is the high frequency radio emission again. The lower frequency radio emission we've already heard traces older bubbles. So the lower frequency radio emission is more extended up towards the north and south in this image. So what's its relation with the cool gas, with this cool ionized phase? This is the morphology of the H-alpha emission in ABEL 4581. So you can see it extends pretty much the whole way around these central lobes. They're pushing out this coal gas, and it extends off to the north and south, and in fact points towards these outer X-ray cavities. So this gas is being pushed around by the AGM feedback, it's being uplifted, it's being moved. This is IFU data of the central parts of this system. So these are line of sight velocities, and the line of sight velocities in these filaments are typically quite low. Line of sight velocities along filaments are typically very smooth. There's possible evidence for rotation in the cores, but these velocities are low. The velocity whips in these systems are again pretty low. There's maybe evidence in this particular system, but we don't often see it, of some sort of outflow, which is of higher velocities. So this red part in the middle, that's about 500 kilometers per second, but the rest of this emission has velocity whips of about 100 kilometers per second. So these are very kind of low quiescent things. They're not high velocity outflows from these AGMs. So this, just to flash up, these are two systems where people have looked with ALMA, higher redshift systems, and they see the same see these same faster velocity outflow that we saw in this individual system. But these are rare at the moment. We haven't got a lot of these for the radio mode feedback. And an extreme example of this coal gas redistribution by AGM feedback is NGC 1225. So in this system, we've got about 10 to the 10 solar masses of cold molecular gas, and it's extended up to about 70 kiloparsecs out of the galaxy. So this really is extreme redistribution of the cool and cold gas in these galaxies. And Jay's going to talk more about NGC 1225 tomorrow. So I'm going to move on and talk about where this cool and cold gas originates from. And to answer this, we undertook a study of 8 nearby brightest group galaxies. So these 8 galaxies all have similar star formation rates, stellar masses, halo masses. They're very, very similar. In their X-ray properties, they have the same X-ray mass. 6 of the 8 have extended H-alpha emission, and there's the 6 that you see here. So 2 of the 8 have no evidence for any H-alpha emission at all. We undertook a Herschel study to try and look for the cold gas phase. So are these systems not forming stars because there just isn't any cold gas, or are they not forming stars for some other reason, something that's preventing this cold gas from forming stars? So in the 6 of the 8 cases where we see the ionized extended gas, we also see cold extended gas emission. And this gas traces the morphologies more or less, but you can see that the pixel size of Herschel is pretty large compared with our optical narrowband H-alpha imaging, which is the black contours below. But importantly, they have the same kinematics as the ionized gas. So again, these two systems know about each other. They're probably embedded in each other. Yeah. So I said that the systems are very similar in terms of their masses and the stellar populations and things, and they are. And they're similar in terms of their X-ray gas masses. But it turns out, if you look in detail at thermodynamic maps of these systems, they look very different in the X-ray. So all of our coal gas rich systems are very morphologically disturbed in their X-ray emission. So they have, these are X-ray pressure maps, and it's the high pressure and low entropy gas that you see following similar morphologies to the filaments in these systems. If I switch over now to the coal gas pore systems, these are very smooth. They're very smooth in their pressures, they're very smooth in their entropies. And these are on similar scales. So you can see I'm not duping you to the size scales.
What are the masses of the cold gas?
Of the cold gas, we're talking about 10 to the 8. 10 to the 7, 10 to the 8 solar mass of the molecular gas. But it does have some assumptions in there about conversion factors, which are not certain. So their X-ray properties vary whether they have the cold gas or they don't have the cold gas. So the hot and cold gas phases know about each other here. And not only are their morphologies disturbed, but it turns out that cold gas-rich systems have a systematically lower entropy. So this is the X-ray entropy, again, that we're showing on the y-axis. So this is the temperature divided by the density to the 2/3. The cold gas poor systems have a systematically higher entropy in their outer regions. So their X-ray thermodynamic property is very different. And what's the link between the cold and hot gas? Well, you can define something like the field stability parameter, and you can look at maybe how this changes in the two groups. So the field stability parameter here is the ratio of conductive heating in the hot gas to the radiative cooling in the hot gas. So a ratio of less than 1 would tell us that radiative cooling is dominating over conductive heating, and a ratio greater than 1 would tell us that conductive heating is dominating over the radiative cooling. And we can see that in all our cold gas-rich systems, we have a field stability parameter that's less than 1. And in all our cold gas poor systems, we have a field stability parameter that's greater than 1, so is in the situation where heating should be dominating cooling. Now, this isn't saying that conductive heating is necessarily the answer for how this heating is happening. But what's interesting is that there's a dichotomy in these properties. Okay, so there are error bars in the lines. Did I have error bars on the... So this is the error bars on the entropy plots. But the dichotomy basically arrives in this parameter because of the dichotomy in the entropy. So what we'd say from this dichotomy then is that the cool and cold gas in these systems likely originates from firmly unstable cooling out of the hot gas. It's likely originated from effectively the cooling flow. So turning back to the AGN in these systems, we can look at the power input to the ICM from the radio mode feedback. So the same way Christoph told us before, we look at this PV energy going into, which we calculate from cavity powers. And what we actually find is that the cold gas poor systems have high jet powers, and the cold gas rich systems have low jet powers. So this is slightly counterintuitive. We might expect that cold gas rich system would have a higher density down by the AGN, and you'd get higher mass accretion rates, and you should get greater powers. But this isn't what we see in this very small sample. So what could be happening here? So we seem to have these two states. Even in these X-ray bright, cool quadrant elliptical galaxies, we still seem to see two states. We see the large jet power systems without cold gas and very relaxed X-ray properties. We see systems that have small jet powers, they have many X-ray cavities which lead to this disturbed morphology, and they have plenty of cold gas, they're cold gas rich. So might these states be an evolution? Might they be a cycle perhaps? Could it be that the AGN outbursts are destroying the cool and cold gas in these systems? As they do, the working surface, then they're working against the hot gas and not the denser cold gas. So the jets can propagate farther into the intercluster medium. They can deposit the entropy then at greater radii, which would explain also the entropy difference that we see at the greater radii. But then, and then the centers would be able to relax again. If the centers relax again, presumably we would expect the centers, the cluster gas to be able to cool again and settle back onto the AGN, and maybe the whole system would be set off again. So I'm going to leave you just with a summary. The cool and cold gas can be plentiful in X-ray bright massive galaxies, but not necessarily in all of them. It's not necessarily the case that every single X-ray bright or cool core thing has a lot of cool and cold gas. So the gas that's there likely originates from cooling from the hot interstellar medium. We see these two states, these cold gas rich and cold gas poor states, and radio mode feedback here is coupling to both the hot and the cold gas in these systems, and maybe quenching star formation from the cold gas from these systems. So I'll leave it there.
Frank, okay, Frank.
I got confused. Initially, you seemed to be saying that you were seeing gas that was uplifted out of the galaxy by bubbles and stuff.
And now I'm saying it's
And now you're saying that it's probably gas that cooled out of the hot air.
So I'm not saying that the filamentary morphology is due to the gas cooling out. I'm not saying it's cooling out into these filaments. I'm saying that there's a reservoir of cool and cold gas in these systems, which likely originated from the hot gas. And then due to the AGM being switched on, due to these bubbles forming and the turbulence also that's generated, the filamentary morphology occurs as the gas gets uplifted, dragged out of the galaxy.
Why can't it just be because when I start blowing bubbles and compressing gas, and at compression I'm enhancing the cooling, and therefore I promote this cooling out of gas at the filament, at the boundaries basically of my bubbles. And that's sort of what
So-
you see. So it sits there at the boundaries of the bubbles.
Yeah, so we don't see, we do, like the systems that we didn't see the cold gas in, they do have bubbles. They have the bubbles, they have the radiojets. We don't see any cooling around those bubbles coming out, at least to the very cold phases. So the gas that's surrounding these bubbles is really gas that's been, the bubbles flown into the cooler phase, and it's surrounding it that way.
Okay, Roman.
In your dichotomy plots, what diffusion coefficient do you consider?
Sorry, but
In the dichotomy plots, where you introduce the diffusion,
yeah, the conductive.
what coefficient do you consider in this plot?
I can't remember the number of the conductive opacity. You mean? I can look it up, but I can't remember it off the top of my head.
Is it pure Spitzer?
Oh, it's Spitzer.
Yeah, 100%, or is it reduced?
No, it's not a third. It's that one's pure.
100% Spitzer?
That one's pure Spitzer. So they've looked at this also in some massive clusters, and there they found a dichotomy, but they found that the field stability parameter was about 5, and they say they need to reduce it then, so they invoke the reducing from Spitzer. We didn't need to. I mean, we see a dichotomy. It's not necessary then that this is the exact mechanism, but the interesting part is the dichotomy.
I'm not sure I caught the reason why you think that there isn't star formation going on. You have a lot of H alpha and things. I know some of this is cooling, but
So we have they have star formation rates. Obviously, like people have looked at the star formation in these systems. The star formation is very low in these systems, but also any like emission that you might think might trace young stars, UV emission and things. They've always centrally peaked on these systems. I'm sure these systems probably have some small amount of star formation, but they very, very, very rarely follow filamentary structures. Now in NGC 1225, they do at large radii. So in that system, you've got star formation going on in the filaments. You can see beautiful morphology of the filaments, but we're talking 20 kiloparsecs out of the galaxy then, and kind of away from where all this turbulence and mess is going on.
Okay, Joe.
Short and related, what is the current, maybe you said this, but what's supposed to be powering nebular emission? Is that supposed to be conduction from the hot phase, or is it plasma radiation from the pure AGN?
So there's no, I would say the general consensus is that there's some sort of particle heating. This is what produces the spectrum. But there's no, people are still arguing about this an awful lot. So it doesn't look like it's photoionization. If you fold in all the optical emission line ratios and also the infrared that we've got on the molecular gas lines and things, it doesn't look like it's photoionization. It doesn't look like stars could do it unless they're extremely, very, very hot. So these warmer systems that people described a long time ago. The emission lines don't fall off away from the AGN. It's not the AGN photoionizing these things. So we think it's probably excitation from the hot gas, but it's a collisional excitation. That seems to produce the spectrum best at the moment, but it does have some hiccups when you come to the very, very cold gas lines.
Okay, is that Brent? You got this?
Yeah, I'm not sure why you think that all the C2 is associated with cold molecular gas when you have, you expect a large fraction of the C2 to come from the ionized phase along with the H alpha and N2. But to help you with also that it's collision involved, you expect strong C2 relative to H alpha and some of the optical lines in slow collisional media as well.
Yeah. So in those systems that I showed at the end, where we had the Herschel lines, we don't have the spatially extended CO or something like this. We don't have the cold molecular gas. So we're tracing, when I was showing those, I should have said, not molecular gas, I should have said we're tracing cold gas about 100 Kelvin. But in other systems that you see this molecular gas, in 1275 again, you see they're beautiful H2 maps that just extend up, same as the ionized gas phenomenon. It's really nice.
All right, thanks a lot, Rebecca.